Hello and welcome to today's lesson on the conservation of momentum. Our plan for this lesson is as follows. We will begin by exploring the concept that, similar to energy, momentum is conserved in a closed system. The total momentum before an event is equal to the total momentum after the event. Next, we will learn how to represent this principle mathematically and apply it to several practice questions. So far, we have understood the relationship between force and momentum, emphasizing how momentum changes when a force acts on an object over a period of time. With this foundation, we can now delve deeper into the principle of conservation of momentum. To start, let's remind ourselves that momentum is a vector quantity, which means it has both magnitude and direction. It's calculated using the formula momentum equals mass times velocity. We can now develop a solid understanding of the principle of conservation of momentum. This principle states that in a closed system, meaning no external forces are acting on it, the total momentum before an event is equal to the total momentum after the event. Let's visualize this with a game of billiards. Imagine ball A moving towards a stationary ball B. When ball A collides with ball B, a fascinating thing happens. Ball A transfers some of its momentum to ball B. You'll see ball B start to move while ball A slows down. In reality, the collision looks like this. We can see the ball which is moving hits the stationary ball, passing its momentum onto the stationary ball, which now starts moving. Let's break this down further. Before the collision, ball A possesses momentum because it's moving, and ball B has zero momentum because it's stationary. During the collision, momentum is transferred from ball A to ball B. After the collision, ball A slows down and ball B starts to move. But the key takeaway is that the momentum of both balls before the collision is equal to the momentum of both balls after the collision. So how can we represent this as an equation? Well, the equation representing the conservation of momentum looks like this for two colliding objects. Total momentum before collision equals total momentum after collision. In this case, we have two balls that are colliding. So the total momentum before the collision must be the momentum of ball A plus the momentum of ball B. Similarly, the total momentum after the collision is just the momentum of ball A plus the momentum of ball B. Let's break this down further. Recall that momentum equals mass times velocity. Let's use this fact to write the initial momentum of A as the mass of A times the initial velocity of A. We can then do the same for the initial momentum of B, the final momentum of A, and the final momentum of B. Great, so we have broken down the principle of conservation of momentum into a mathematical expression. We can now use symbols to make this even simpler. Using m to represent mass, u to represent initial velocity, and v to represent final velocity, we can now write the expression like this. Now that we have learned how to represent the conservation of momentum mathematically, let's apply this knowledge to a few specific problems. Problem 1. Imagine cart A collides with a stationary cart B on a frictionless track. We have the following information about the carts. The mass of cart A is 2 kilograms. The initial velocity of cart A is 3 meters per second. The mass of cart B is 3 kilograms. And the velocity of cart A after the collision is 1 meter per second. Our goal is to find the velocity of cart B after the collision. Step 1 is to write down the given information. For this, it can help to use the mathematical notation we just discussed. So, starting with the information we have been given about cart A, we have that the mass of cart A is 2 kilograms. The initial velocity of cart A is 3 meters per second, and the final velocity of cart A is 1 meter per second. Now for cart B. We know that the mass of cart B is 3 kilograms. We have also been told that cart B is initially stationary. This means that its initial velocity must be 0 meters per second. We don't know the final velocity of cart B. This is what we need to find out. Step 2 is to use the conservation of momentum equation. We know from the principle of conservation of momentum that the total momentum before the collision equals the total momentum after the collision. This means that the initial momentum of A plus the initial momentum of B equals the final momentum of A plus the final momentum of B. As we just discussed, we can represent this mathematically like this. Step 3 is to substitute the given values into the equation and solve for the final velocity of B. Substituting these values in, we get 2 kilograms times 3 meters per second plus 3 kilograms times 0 meters per second equals 2 kilograms times 1 meter per second plus 3 kilograms times the final velocity of b. Now we can simplify each of these brackets. The first bracket simplifies to 6 kilogram meters per second, and the second bracket simplifies to 0. So we are just left with 6 kilogram meters per second on the left of the equation. On the right-hand side, we get 2 kilogram meters per second plus 3 kilogram meters per second times the final velocity of cart B. Now we can solve for the final velocity of cart B. First, subtract 2 kilogram meters per second from both sides of the equation. This leaves us with 4 kilogram meters per second equals 3 kilograms multiplied by the final velocity of B. Since we want to find the final velocity of B, we can divide both sides of the equation by 3 kilograms. This leaves us with final velocity of B equals 1.33 meters per second. So the final answer for this question is after the collision, cart B moves with a velocity of approximately 1.33 meters per second. Now let's look at problem 2. Imagine we see two ice skaters pushing off each other after being stationary. We have the following information about the skaters. The mass of skater A is 50 kilograms. The initial velocity of skater A is 0 meters per second because they are initially at rest. Skater B also has an initial velocity of 0 meters per second as they are also at rest. We are also told that the mass of skater B is 75 kilograms and that after the push, they have a velocity of 2 meters per second. In this question, we want to find the velocity of skater A after the push. Just like the last question, the first step is to write down the given information. Using the mathematical notation also helps here. Let's start with the information we have been given about skater A. We are told that their mass is 50 kilograms and their initial velocity is 0. Their final velocity is the unknown that we are trying to find in this question. Now for skater B, we know that their initial velocity is also 0, that their mass is 75 kilograms, and that their final velocity is 2 meters per second. Step 2 is to use the conservation of momentum equation. As there are no external forces, the total momentum is conserved. This means that we can use the equation that initial momentum of A plus initial momentum of B equals final momentum of A plus final momentum of B. Step 3 is to substitute the given values into the equation and solve for the final velocity of skater A. Inputting the given values, we get the following. Now we can simplify this. We can see that the left-hand side of the equation simplifies to 0, and the right-hand side simplifies to 50 kilograms times the final velocity of A plus 150 kilogram meters per second. By subtracting 150 kilogram meters per second from both sides, we get this. And then we can solve for the final velocity of skater A by dividing both sides of the equation by 50 kilograms. This gives us an answer of minus 3 meters per second. So the final answer is that after the push, skater A moves with a velocity of minus 3 meters per second. Great work! That's the end of our lesson. Let's quickly recap. Today, we delved into the principle of conservation of momentum, where we learned that in a closed system, the total momentum before and after an event remains constant. We explored this concept through examples such as a game of billiards, where a moving ball collides with a stationary one, transferring momentum while maintaining the total momentum. We also explored how this principle can be represented mathematically and used it to solve problems. Watch the rest of the GCSE physics course at Sophos Education.